Today we are going to see how the signal is represented in the signal space using Schmidt orthogonalization. So we are taking the example here for a polar signal. So aim is Schmidt orthogonalization. For baseband signal, it is a polar signal in the form NRZ, non-return to zero, and later on will be calculated during testing. So the signal here, which is the polar signal, is basically represented in the form as S1T, which is having magnitude of plus A in the interval of the T is varying from less than or equal to 0 and greater than or equal to 0 is the representation of one bit. If the bit is in the form of 1 and the signal S2 is represented as minus A, which is again in the interval of 0 and TB. It is the representation of bit as 0. Bit as 0. And it is called bit as. Once the bit is being represented and it is being marked here as the capital A, in the interval the signal is in with respect to timing and it is plus 1T and magnitude of that signal is plus A and signal S2T will have a magnitude minus A and it is with respect to 0 and TB and this signal is S2T. Now the signal polar signal which is represented in the form of S1T and S2T, and we all have seen they are not independent of each other, means S1 can be represented in terms of S2 and vice versa. So we need only one orthonormal basis function and base S1T is written as S11 phi1 because very first signal and we are representing that in the term of orthonormal basis function and the basis function is only one here, that is phi1t. So phi1t, the orthonormal basis function is represented as 1t upon the normalized value of S1t, which is nothing but the square root of energy of the signal S1t and written as under root of energy E for the signal S1. Now, what is energy E for the signal S is calculated as E of S1 equal to the signal which is present between the duration of 0 to T. All of us can see the signal is in the interval of 0 to T and the magnitude of the signal S1 is E square dt, which can be multiplied as E square 0 to T 1 into T. And integration of 1 is with respect to T is T 0 to T, which can be further represented as T square upper limit, lower limit, and the value is coming as T square T. Now, phi1T is represented as signal S1T divided by square root of energy of the signal and which is T square T right now, which further can be written as the signal S1T is a unipolar signal and it is having magnitude A between this interval. So phi1T can be written as magnitude A of the signal S1T and the energy of the signal TV, which is nothing but 1 by root TV, and it will exist between the interval of T is greater than or equal to 0 and less than or equal to TV. A value will get cancelled. Now, as we can see, if we draw the diagram for phi 1 t, so the orthonormal basis function phi 1 can be drawn as the magnitude value is 1 by root 2v, and the duration is same as the signal S1. This is graphical representation of orthonormal basis function phi 1 t, and it is with respect to the t, not need to be written as phi 1 t. It can be written as t. Now we'll see what is S11. As S1 we know, phi 1 also we know. So what is the projection of S1 on phi 1? So we will now look for S11. We look for S11. So S11 is projection of signal S1, the projection of signal S1 on phi 1. If this is S1 signal, so projection of this signal, this is a vector, projection of this on phi 1 is called as S11, where this is for the signal 1 is for the basis function, orthonormal basis function phi 1. So in this way, S11 can be represented as the common area between the signal S1t and the signal orthonormal basis function phi 1t. As we have seen previously, the signal S1 is in between the, if I draw here signal S1t, then we'll come to know here that the common area between the signal and the basis function is between the interval 0 to dB. And the magnitude of signal S1 is A, and the magnitude of phi 1t is 1 by root of dB, dt, which can be further calculated as A by root of dB. Integration of 1 is written as t, and the lower limit and the upper limit, which can further be simplified as S11 equal to A by root dB into dB, and can be simplified as dB. So this is S11. Now we will be looking for the signal S2. So signal S2, now we will be analyzing the signal S2 as for signal S1, which was written as S1t is equal to S11 into phi 1, and both the unknown parameters are known to me now. And if you multiply together both of A root dB, which is the information about S11, and phi 1t is having information as we have calculated before, and phi 1t is equal to what phi 1t is what? Phi 1t is equal to 1 by root dB, as we have calculated before. So the signal A, which we have mentioned before only. It means whichever the calculation we have done so far is proper. Now we are looking for signal S2, and signal S2 is equal to, it can be written as S21 phi 1. As we mentioned previously, we are only having one orthonormal basis function, but two signals are not independent of each other. It means S2 can be represented in terms of S1 and vice versa. This is the relation between S1 and S2, and they are not independent. They are dependent on each other. So phi 1 we know from the previous equation. Now we are looking to the projection of signal S2, projection of signal S2 on phi 1. That is what is S21 says in this first lecture. So how this value will come, that we will be calculating based on the area covered between S2 and phi 1. So the area of S2 is between 0 to T, and the magnitude of H2 is minus A. As we have mentioned, it is representing for the 0th bit, and the area of phi 1 is represented as 1 by under root of TB between the interval 0 to TB. Further written as minus A by 2 TB outside, and the integration as it is again between the interval 0 to TB, and it is minus A to TB. So what we concluded here from so much calculation is S21 and S11 both has come, and they both are projecting on the orthonormal basis function phi 1 t. S21 is having the value on the phi axis is minus A root TV, and S11 is having magnitude plus A root TV, as we have calculated before. S1 is S11. S11 was root TV, and S22 just now we have seen S22 is minus. Based on this, you can see here that the distance between the two is Euclidean distance, and for that to calculate, if we take this in the form of vector coordinate, so A root TV 0, and this value x coordinate and y coordinate 0, because the orthonormal basis function phi 2 exists. So B12 is equal to minimum distance formula, it is Euclidean distance, first function minus second function whole square, and second function minus first function whole square. So we'll see that that value should come as 2A root 2 root TV. So first component x1 minus x2, A root TV first function minus A root TV, x1 minus x2 coordinate whole square plus y1 minus y2 coordinate whole square, as both y coordinate is 0. This value can be written as 2 times of A TV whole square. Nothing but 2 root TV of Euclidean distance. So we have seen the representation of polar in the last question diagram, and the distance is S2, and this is S1, and value is 2A. This is overall representation of our polar signal in the form of orthogonal. That's all.